Hi there. I want to talk a little bit more about the atmosphere. I want to talk about the movement of air parcels, known as the circulation. Because you need to understand that for a number of reasons. We're talking about the reasons as to why there are regions where you have large amounts of rainfall and why there are regions where you have very little rainfall. And it's all to do with the atmospheric circulation. So, this lecture has 3 parts. Okay, Part A talks about key features. We talk about the average circulation patterns in the atmosphere, and we talk about vertical circulation cells. And you will understand the significance of these vertical circulation cells. They include the Hadley cells, driven by the intertropical convergence zone, the Walker circulation, the monsoon circulation, and land and sea breezes. And they're all related with the formation of rain zones on Earth. The second part talks about the surface wind patterns. The surface wind patterns. So they're not much changing from one year to the next. So we can actually name wind systems. And there's also seasonal variations known as monsoons, and you will learn about that too. The last part talks about other features, which includes tropical cyclones, polar fronts, and the generation of extratropical cyclones, also talking about mountain shadows. And there's the link here to extreme events, to storms. Okay, so this is a big lecture, but there are no equations, but there are important concepts that I want you to think about. So let's talk about the key features. The key features of the atmospheric circulation. And the best approach to learn about this or to understand the circulation is to imagine that you have an Earth which is not rotating. And which is shown here, a non-rotating Earth. Because with the rotation you get an additional effect which is known as the Coriolis force, but we just ignore that for the moment, So you learned that the Earth is warmer near the equator and colder, the surface I'm talking about, and colder near the poles. So this gradient in the surface temperature now creates so-called convection cells in the atmospheric circulation. So it's a closed pattern of movement which is initiated near the equator with rising air masses near the equator, then a flow at height towards the poles, and a return flow of air parcels along the surface towards the equator. So you get a surface flow towards the equator, feeding the rising air. And that's an important principle regarding fluid motion. If you have a movement away from a region, you get compensating return flows. And that's a very important principle. All right, so just to summarize, the heating from below in equatorial regions creates circulation cells in both hemispheres, rising air along the equator, fed by equatorward surface winds, and you have downward air motion at poles. So now, with the rotation of the Earth, there are changes. And the most significant change, due to the Coriolis force, is that instead of one circulation cell in each hemisphere, you actually get 3 cells. It all starts with the rising of warm air near the equator. which creates Hadley cells. We actually have now the sinking air at something around 30 degrees north and south, okay? That limits the extent of these cells. And you have counter-rotating cells which have poleward airflow near the surface and a return flow at height. And in polar regions you get polar cells, okay, which again have a different direction. This is the first important feature. Okay? The second part is that you actually get zonal winds near the surface. Also at height, but it's because of the Coriolis force, the dominant air motion is actually from west to east or from east to west. This is what we call zonal. So near the equator you get the trade winds. Okay, they still have a component towards the equator which feeds the vertical upward motion in these areas here. And you get westerlies, which are zones of strong winds from west to east. Okay, it's called westerly, is the wind that comes from the west in both hemispheres. Now you have westerlies in the northern hemisphere and westerlies in the southern hemisphere. Okay. What you also get is you get a new zone which are called polar fronts, okay, which are triggered by these surface winds which come from the poles. You get very cold air from mid-latitudes, lower latitudes. You get warm air, and it forms something which we call a front, okay, which has a strong meridional temperature differences. And these fronts actually create weather patterns. They create the storms that we have. They create extreme events. Okay, that's the second important feature. The third important feature is that you have upward or downward motion. Okay, and the upward motion through something we call atmospheric convection creates clouds and rainfall patterns. Okay, and this is illustrated here in this as well in this sketch. Okay, that's the third very important feature. We talk about that on the next slides. So we have vertical circulation patterns and we have horizontal winds. And they both operate at the same time. It's a little bit tricky to imagine, how that, because it's a dynamic system or so. And so the horizontal winds are generally much stronger than these vertical circulation, the vertical motions. Okay. However, the vertical motions are crucial for the formation of clouds. So just a little summary, just reading what's written up here. Heating from below initiates convection and cloud formation in the intertropical convergence zone, the ITCZ. It's this zone along the equator. This is the key driver of vertical circulation cells known as Hadley cells. The rotating Earth creates zonal wind patterns. But this is because of the Coriolis effect, leading to the formation of the polar front. Instabilities of polar fronts trigger the formation of weather systems. Okay, this is quite complex, quite a link to different aspects that we will be discussing in this lecture and in future lectures. Okay, there's a little bit more to it, which is to do with seasonal variations of where the regions are actually where the atmosphere is heated. It's not always in equatorial regions. Okay, but you will learn that as part of the monsoon circulation. Okay, so there are seasonal variations associated with the shift of the region which is heated, where the air is heated from below. Okay, so now let's focus on vertical circulation cells. Not yet. Before we do that, is the key feature is atmospheric convection. Okay. I just go through the steps that are written here because it's really important to understand that. This is an important part of vertical circulation cells. It's the driver of these vertical circulation cells. So what it is, atmospheric convection, it's the upward motion of air generally initiated by heating from below. And that sets off a number of processes. The temperature of an air column increases at the bottom. The air parcel expands, the density of the air decreases, the air parcel rises through the column. You get the upward motion of the air. As the air parcel rises, the temperature decreases, water condenses, clouds appear. As water condenses, latent heat is released, which further drives vertical motions. Continued condensation of water vapor causes precipitation. And that's one example shown here for one process known as tropical convection. You can see the region of the rising air. You know where it is because you can see that cloud formation. Okay, this pattern. And if you're into gliding, you can look at the clouds and you can see where there are regions where you have this uplift, where the vertical air motion can actually lift you up, on your glider. Okay, so now the key summaries. The rising air masses are usually associated with cloud formation and precipitation. On the other hand, the descending or subsiding air masses are usually associated with clear sky and little precipitation. So it's really important to understand that difference between rising and sinking air masses and the link to rainfall or no rainfall. All right, and this brings us now to vertical circulation cells. And there are a number of these vertical circulation cells with vastly different horizontal scales. Okay, there's the Hadley cells, there's the Walker circulation, there are monsoon circulations, and we're talking also about land and sea breezes. So the general structure is shown here in this sketch. Okay, so you have convection, atmospheric convection, rising air, and this leads to a surface wind feeding air masses into that zone of rising air. Okay? And here the important note is, while you need to have moist air in order to create precipitation, so where the air comes from is very important. If you have the connection to the ocean, you get the rainfall. Okay, if it's coming from the inner parts of continents, you don't get any rainfall because you need that source of water vapor. Okay, and then at height you get some return flow, and you have a region where you have downward air motion, no clouds, nothing happening here in this part. Okay, so now let's go through these examples. Okay, we start with Hadley cells. Here we go, Hadley cells shown in a sketch. This shows you the vertical movement pattern, also horizontal movement patterns in these Hadley cells. And we're talking about a region from 30 degrees north to 30 degrees south. Okay? That is what we're talking about. Driven by rising air masses in the intertropical convergence zone. So this rising of air creates a wet zone. Okay, intertropical convergence zone, wet region, wet climate. And the subsidence of air, the sinking air masses at around 30 degrees north and south, creates dry zones. It suppresses the formation of clouds, and it suppresses precipitation. So that's all there is, and this cell exists all the time. Okay, you'll learn later on that the intertropical convergence zone actually is not always centered over the equator. It actually moves. It depends on where the surface is heated more than in other regions. Okay, but the key is that you have this zone. So what's the scale of these cells? Can we just look at it? Well, you can see here the height scale, 10 kilometers, 12 kilometers. It's the vertical scale of these cells, and the horizontal scale is about 30 degrees in latitude. How much is that in kilometers? 1 degree is, what do you think? Do you know that? Okay, 1 degree, around 100 kilometers. Okay, so we're talking about 3,000 kilometers is the horizontal scale. This is what we're talking about. Okay, 3,000 kilometers away from the equator, both north and south. Okay, so let us now look at the Walker circulation. It's a similar thing, but show you on the sketch. This shows you the Walker circulation. Okay. You look at that cell. It actually is a cell along the equator of the Pacific Ocean. Not north-south, east-west. It's a very large circulation cells, and we're talking about a distance of, well, you can come from Australia over to Peru. So we have about, how many kilometers is this? This is a 130, 50 degrees. You know, we're talking about 5,000 kilometers. Okay, something like that. So, and again, this circulation cell is driven by convection. Okay, convection, atmospheric convection on the western side of the Pacific. You know, creates this updraft and cloud formation, you know, and you get the moist air, actually the surface wind, you know, feeding this convection, okay, near the surface. And these winds are actually called the trade winds near the surface. They feed that. Okay, so this is another example. And just to mention it here already, variability of the Walker circulation also includes a coupling with the ocean, actually is linked to the formation of El Nino and La Nina events. Okay, and this is the Walker circulation. All right, we're almost there. We can look at the monsoon circulation. Monsoon circulation is driven by the shift of the intertropical convergence zone over the continent through the heating up of soil during the summertime. Okay, you get again an updraft and cloud formation, but over the continent, and you get the surface winds, which has the connection to the ocean and which is the source of the water vapor that you need for the rainfall, and you get some return circulation at return flow at height. Okay, so again, circulations are but operating on a different scale. On an even smaller scale, you get the land breeze and the sea breeze. Okay. land breeze and the sea breeze systems, which, if you have the surface wind coming from the sea, can also trigger rainfall. But on a much smaller scale, we're talking about 10 to 40 kilometers or so. I think it can reach 100 kilometers or so, as far as I remember. But you also have vertical circulation cells in these sea and land breeze systems. Okay, there we go. That's the very important components to understand being part of the atmospheric circulation. Okay, this concludes the first part of this lecture, all right?